Just like our home atmosphere is subject to violent and damaging storms, such as Sandy, our space environment undergoes violent disruptions driven by powerful flares and coronal mass ejections from the sun. These storms, which define the weather of our space environment, are much more energetic than the storms of terrestrial weather. And the boundary of the Earth's atmosphere and space is in constant flux. Not surprisingly, it is our sun that has the biggest external effect on our atmosphere. Our planet and our star are in a continuous dance. Any object in low Earth orbit, whether it is a deorbiting spacecraft or the International Space Station, will have variations in its trajectories as it interacts with the thermosphere. The main reason for these changes in trajectories is atmospheric drag, changing in response to the activities on the sun. We asked, can we use synthetic machine learning data to improve the modeling of the atmospheric drag? Any improvement on predictions of spacecraft location, likelihood of collision, re-entry prediction, and communication would be of great benefit to the space situational awareness community. Therefore, I am really excited to introduce the work of this team. Solar drag, or really atmospheric drag.
Hello, everyone. Thank you for taking some time off from your schedule to hear our presentation. We are the Solar Drag team. I'm Stefano. I'm the second member of this team. And over these 9 weeks, I worked together with Bernard, with Edward and Jorge, and supported by the 3 amazing faculty members that we had, Giacomo, Gunes, and Chris, supported by 2 research advisors, Mori Baja and Eric Sutton. Our challenge is associated extremely with all of the parts associated with the sun. In particular, we know that for what concerns the lower part of our atmosphere, the population of satellites is continuously growing in time. That is often a problem, especially like the more we go on in the future, the more it will become a problem, because whenever 2 satellites actually intersect their trajectories, they can collide. Whenever they collide, they actually can generate a cloud of debris. This particular cloud of debris is important that we must have to not happen in the future. So in this case, when we form this cloud of debris, we can extremely endanger future accessibility and safety in space, especially for the lower part of the atmosphere, what we refer to as the thermosphere. But what is the main driving factor of all of those satellites and objects orbiting around the Earth? Of course, mainly is the Earth, it's gravitational pull of the Earth. But the secondary force is a perturbative force known as orbital drag. In this case, the orbital drag is associated with the interaction of the spacecraft or those objects orbiting the thermosphere with all of the particles of the thermosphere itself. It is important, especially to characterize the thermosphere, especially the density, so we can estimate this particular perturbative force, again, the orbital drag. Because whenever we improve the estimation for that particular force, we can then improve how we estimate the location of all of these objects, so we can prevent those collisions to happen. The most important challenging part of this particular thing is that the thermosphere and the atmosphere reacts with respect to how the sun emits all of the energy, and all of that particular solar activity interacts with the atmosphere, all of the amount of energy that arrives to the atmosphere, and in this case, to the thermosphere itself. But modeling this particular interaction is extremely complex. So here it is, the challenge that we tackle in our team for the solar drag for this 9 weeks FDL challenge. In particular, we translated this challenge into a question, our research question, which is how can we use machine learning, so a data-driven approach, having all of this information from the sun, arriving from solar indices, as well as image from the sun, ingest all of this information in a machine learning model that we can learn, we can train, such that we can improve our estimation for the orbit drag. And this, I'll hand it over to Edward, which will be introducing to you the first part of the results that we achieved in this 9 weeks effort.
Thanks, Stefano. So the sun emits light and energy that's absorbed in the thermosphere. And in order to estimate the thermospheric density, there's a lot of different data sources that we might use. So in terms of solar imaging, there's images from the Solar Dynamics Observatory, but there's also irradiance data, geomagnetic indices, and things like that. So we want to use these disparate data sources into a machine learning model and estimate the density, as well as outputting uncertainties. So what do our different machine learning pipelines look like? So there are two separate pipelines. So the first on the left is the space weather indices forecasting. So space weather indices are numbers that are used in thermospheric models. So being able to forecast these indices is very important to working out where your spacecraft is going to be, because it tells you how much drag it's going to encounter. So in yellow, we have the different inputs to our model. In blue, we have an ensemble model, which just means lots of different models, which we train together to produce a range of values, which is our uncertainty. And in the red, we have the output. And when we say loss, we just mean how wrong is our model. And that's what we want to reduce. And similarly, for thermospheric density modeling, we have a whole range of different data sources that we'll put into a neural network and be able to output the loss as well as uncertainties in our outputs. But crucially, we really wanted to focus on creating uncertainties in these outputs because it's not often done in space weather forecasting. So I mentioned solar features. What exactly do I mean by that? So here's an artist's impression of the Solar Dynamics Observatory. Now, the Solar Dynamics Observatory has been running since, I think, 2010, and it's been taking images of the sun in 12 channels every 6 minutes in high resolution. So what do I mean by channels? So by channels, I mean like a normal image normally has actually 3 images behind it, red, green, and blue. Now, for the Solar Dynamics Observatory, it's actually taking in 12 channels. And there's the top, as you can see here, there's the top 3, the sort of strange looking ones in the top left are the magnetic field strength on the sun. And the remaining 9 are extreme ultraviolet channels, and they all contain different information from each other. So the idea is to condense these different channels through a feature extractor. And from these, and features just means expressive things about the sun. And we use these extracted features for a downstream task. So I'll pass you over to Bernard, who will talk about forecasting these space weather indices and also how we use these images.
Thanks, Ed. I will now talk about our space weather indices forecasting work. The top left figure shows our simplified ML pipeline for the space weather indices forecasting. We pass as inputs the solar proxies or solar radial flux proxies and the geomagnetic indices to our ensemble of LSTM model and then produce the loss and the uncertainties in predictions. We generate a simultaneous multivariate forecast of the solar radial flux and the geomagnetic indices using this process. The sun has an average of 27-day rotation period. And so we use as input 4 solar rotations worth of input data to produce 1 solar rotation worth of output data that is 27 days. The figure on the bottom left shows our model's performance at the root mean square metric against other simple baselines. The figure then on the right is a sample forecast showing the dotted lines represent the ground truth, the solid lines represent the mean of our ensemble prediction model, and the shaded regions show our uncertainties. Now moving on. On this pipeline, we add the solar image features from the feature extractor to our ensemble model as inputs. So along with the solar proxies and the geomagnetic indices, we're adding the solar image features from the feature extractor to produce our results. And on the bar chart on the right, you can see for the solar indices, there's a 30 to 40% improvement at the R root mean square metric for the solar indices. This shows us that adding solar images as features improves the performance of space weather indices forecasting. And with this, I pass on to Jorge, who will talk about the thermospheric density work.
Thank you, Bernard. So we will now look at our model for the density in the thermosphere. So the thermosphere corresponds to a region in the atmosphere where satellites in low Earth orbit move, and its density determines the strength of the drag on the satellite's motion. So essentially, we're using data from high-calibrated satellites together with solar and geomagnetic activity data to predict the thermospheric density. So how do our results actually look like? So in the top plot, we see the thermospheric density as a function of time. The blue line represents the satellite ground truth data that we're trying to predict. The red line represents our actual prediction, and the shaded region is the uncertainty in our prediction. On the other hand, the yellow and black lines correspond to predictions from state-of-the-art empirical models. And what we see is that our model is able to accurately reproduce the thermospheric density values from the ground truth data. Now, in the middle and bottom plots, we show error metrics for prediction. Those plots show that our model is doing a pretty good job in predicting the thermospheric density. And next, we ask, how does the reconstruction of the global thermospheric density field actually look like? So on the left, we see the thermospheric density field reconstruction from our model. And on the right, we see the thermospheric density field from a state-of-the-art empirical model. And we see that our model is indeed able to reproduce the structure in the thermospheric density field. So being able to tame the thermospheric dragon. So with all these exciting results, we can now try to summarize our results so far. So we've been able to produce some space weather indices forecasting, and we also produced a thermospheric density modeling. We have provided uncertainty in our predictions, and we have been combining multiple data sources. And with this improved forecast and drag estimation, we're in a place to provide more precise orbit estimation for spacecraft, as well as for assets that are important for space agencies. So we would like to thank NASA, Google Cloud, UCAR, and all of our partners. We would also like to give special thanks to all the researchers that gave us incredible feedback and support. And finally, we would like to give a huge thanks to our awesome faculty, Gunesh, Giacomo, and Chris. Thank you all for all your support and hard work. And thank you very much for listening.
Well done, Solar Drag team. And we'll go ahead and bring up our panel and Bill to host our Y panel.
Great. Well, that was really amazing. And I have to say, and I don't think I'm really overstating it here, you had sort of two challenges going on at the same time, where you had two different problems converging. One was developing this improved predictive modeling of the sun's behavior, but the other understanding its impact on the thermospheric density, and then ultimately that helps us with more accurate predictions and understanding of spacecraft and satellite orbits. So joining us, Scott and I, to help unpack what this team achieved is Mark Chung, who is a senior staff physicist at Lockheed Martin. And like Scott and many others here today, Mark has been working with and supporting the FDL program now for many years. So Mark, thanks for coming along and joining us, and tell us your perspective of what's been achieved here.
Thanks, Bill. Hi, everyone. So first of all, I would like to congratulate the team for the astounding productivity that you had in a short amount of time during the summer. You had a set of very impressive results that unfortunately, because of time constraints, you couldn't go into detail. And I have so many questions in my mind. I'm sure we will catch up offline. But I want to frame the type of work and the importance of your work for our audience here. Imagine if you're going out on a boat trip and you didn't know how to predict the tides. That is sort of what's going on right now when we send our satellites up into space. We're not very good at predicting the atmospheric density in the high atmosphere and to predict what sort of atmospheric drag our satellites would experience. And then we decide, okay, let's send fleets of thousands, hundreds and thousands of our ships into space, still without knowing how to predict the tide. So this is why it's so important for us to be able to do so. And in the past, people have been using a so-called F10.7, this radio proxy, because that was what was available. But since Solar Dynamics Observatory and continuing on with the SUVI instruments on the NOAA ghost satellites, we're going to have decades-long observations of the extreme ultraviolet output of the sun, which is driving the changes in the thermospheric density. The model that you apply here, the models you have trained here, is not only relevant for the near future, it could have potentially an impact over the next decades. It really could change the next generation of how we do modeling and predictions of atmospheric drag. So I applaud you for taking on this big task and having such a good results.
Thank you, Mark. I couldn't agree with you more. Scott, so we're seeing a consistent theme here in terms of AI and ML tools helping us not only better understand and characterize phenomena, but also develop these predictive models of what's going to happen in the future. Where do you see this kind of work going of the sort that the Solar Drag team did?
Well, I don't know why we don't have space weather. I mean, we need Mars weather, Titan weather, and the journey. And we don't venture out, as you said, Mark, into the seas until we know what's going on, right? Same thing for flying. And I think that's just going to be normal in the next decade or two, right? As you're venturing out as a human race. And this is just magical to me, Bill, because we take these enormous cloud compute, and that is just a tool for these individuals. And what they're working on is something I see in everyday business, which is sensor fusion. Because what's interesting is these highly complex models we put together can fuse multiple different things that we struggle as humans to understand, and then produce conjectures that we can then go test through a scientific method. I think that is also a hallmark of what we're seeing with AI. And it's just, hats off to the team. Fantastic result. I love how you sort of show the magic of a cloud applied to science. And I'm just learning from you. So great work. Thank you.
Well, it's interesting what you say, Scott, because it's like we try to break things down when we understand them. In understanding them, we're trying to predict what's happening next. What are sort of primary influences and secondary and then tertiary. And what you're saying, if I'm understanding you correctly, is that AI and ML have the opportunity and the ability to synthesize all of these at once, the major effects, the subtle effects, and understand how they interact instead of, deconstructing them the way we tend to because of our limited capabilities. So really fantastic.